Hello, this is a follow-up video to one-way fixed effects ANOVA part 1 of 10, which we called model development. And the idea here is we're going to illustrate the ideas that we cover in each part. And so we're going to look at part 1 first. The example we're using is from Montgomery, Design and Analysis of Experiments, 3rd edition. We're going to look at example 3-1, which is the tensile strength experiment. They describe it as an engineer is interested in determining if varying the cotton content of a synthetic fiber affects the tensile strength. Tensile strength is how much force is needed to tear the material. And they have a run, and they run a completely randomized experiment with 5 levels of cotton percentage and 5 replicates. And so here are the data, and I load it into TSE, which is Tensile Strength Experiment. And so to look at the data, it's this. And so C15 stands for 15% cotton in this particular fiber. C35 is 35% cotton in that particular fiber. Let's look at the column sums and totals, or means, the sums and means. So this is the average tensile strength when we use 15% cotton. 10.8 is the average tensile strength when we use 35% cotton. You can kind of tell that it goes up and up, up, and then we use too much cotton and it goes back down, which is interesting. Now, in most of what we do, we need this in what's called long format versus wide format. Here, each column represents a percent of cotton used in that fiber. So let's reshape it, and there's a R function called reshape, so we can reshape it to long format, which we get here. Now, ignore the row names. That can often be frustrating in an R. But we have a treatment, which represents C15, C20, and then the actual tensile strength that we obtained, when we conducted the experiment. Now I want to create a design matrix for this. Now, you wouldn't need to do this. You just run ANOVA or AOV on these 2 columns and everything is fine. But we want to illustrate the ideas in the video. And so that's why we're creating a design matrix. Now the first column or row here, I create a vector of 1s and 0s, and then I use those to create the design matrix. And so here's the design matrix. And so the first column is 1s, and that represents the mu parameter, and then the next 5 columns represent, it's 1s for treatment 1. In this case, it's the 15% cotton strength, 20%, 30, and it goes down. And so these would represent tau 1, tau 2, tau 3, tau 4, tau 5. Alright, so let's look at the dimensions of our design matrix. It should be 25 by 6, yep. Now the rank should be 5, because if we sum up these last 5 columns, it equals the first column. And so it's a dependent vector. So the rank is 5. Now in this video we created a perpendicular projection matrix onto the column space of 1s. And you do this by whatever column space you want to span. So in this case it's the 1 vector. You take 1 times 1 transpose 1 inverse times 1 transpose. And that's what this function or this command represents. Now in later videos we create what's called a U vector. Oh, so let's look at J. So J is a constant vector of this. And I'll explain what that is more in a second. In some of the latter videos, we create what's called a U matrix, and it's really a matrix of all 1s. So it's the same dimensions, 25 by 25, but that goes first. So then we divide the U matrix by 25, or n times a, if you're going back to the video. So if we look at U divided by 25, we actually get the J matrix. And so if and the divide by 25 is really this piece right there. So the solve of 1 transpose 1, if we just run that, we should get 0.04. And so that's what's creating that divide by 25 piece. It is a projection matrix, so J times J is J, and you can see that. Now the rank of J should be 1. Yep. And since it's idempotent, the rank is actually equal to the trace. Now the trace is you add up the diagonal elements, and that's what this command does, and we should get 1, and we do. Now let's look at the projection matrix onto the column space of M. Now we need the mass library for the generalized inverse matrix, but technically we don't need it. We can get around it, and I'll show you in a second, or the next. So let's load it, and that's so we can run this generalized inverse of X transpose X. Okay. And if we look at this, let's just run this. I didn't store it in anything. The generalized inverse, becomes sort of numerically clunky, and even if we look at this, 1.3 times 10 to the minus 17th, that's pretty much 0. But it stores it like this, 2.0 to the minus 1, so that's 0.2. If you were to go through this, you would see that it's essentially a block diagonal matrix. But we're not going to do it like that. In the video, I showed that if we get rid of the first column of all ones and then rerun it, actually X transpose X is a invertible matrix, so we can just use the inverse. So it's the solve command in R. And when we do this, and I didn't store it anywhere, then it becomes much nicer. And notice here we get block, and this is 1 over 5. This is 1 over 5. Let's go up a little bit to the beginning. So here we have a block of 5 by 5, and the next block of 5 by 5, and it's all 1 over 5, and that's because the number of replicates in each treatment was the same. It was 5. Now, if we remove the first column of X, right, because that's the dependent vector, and then we use the generalized inverse instead of the inverse, it actually, because it's a full, it's a non-singular matrix, the generalized inverse is the inverse, and we get the same thing. And I'm going to run it with G inverse instead of solve, and I'm going to store it to M, but notice that it's the same as if we used the inverse. M times M, we get it back, so it is idempotent. If we look at the rank of M, it's 5. Remember, this is a 25 by 6 matrix, but it has rank 5. And since it's idempotent, the trace is actually equal to the rank. So let's add up the diagonal elements, and it is 5. Now, in part 1, we didn't look at the identity matrix. We didn't do anything with it, but I'm going to create an identity matrix. We're going to look at the rank. And since the identity matrix is idempotent, it should equal the trace. And there we're just adding up 25 1, so it is the same. Now, in the video, we did look at M times Y. Now, Y was the response, or the dependent variable. So and just to keep our notation the same, I'm going to put the tensile strength, response in a variable called Y. And if we look at M times Y, remember M is a perpendicular projection matrix, so it's going to take that Y, which I sometimes call a dangling Y to illustrate that it's out in space somewhere. M is going to shove it into the column space of X. And let's look at that. And so the result's down here, but I also want to just print out the means of each group and show you what M times Y. And we call it the treatment mean vector. So notice the mean tensile strength in 35 is here. Mean tensile strength of 30 is the next kind of group or cluster, and then it's 17, and then it's 15, and then it's 9. So that does create a mean vector in a unique format, and so it's actually important to understand that. Now let's look at the grand mean. So we take j times y. Now j is a perpendicular projection matrix on the column space of ones, so it's going to take that dangling y vector and shove it down into the column space of 1, which is a constant vector. So if we look at that, we calculate it. Now let's just calculate the mean, and notice that it's a constant vector 15.04, which is the grand mean, and that's what we call the grand mean vector. And this is all we have for part 1. And so stay tuned for part 2. And as always, I will put this code for part 1. I'll copy it and paste it into the comment section so you can play around with it if you want. That's all I have. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.